Hi, we are the Group 1. We are going to present the science simulation of a centrifugal pump. What we will present today will be objective, introduction, geometry, mesh independency, physics, results, and conclusions. Objectives. The aim is to design and simulate a pump that meets specified requirements, adhering to the stand nomenclature and determining its operating curve. The project involves recognizing physical models governing pump operation, sketching the geometry using CAD program, simulating its performance using CFD software, and analyzing results compared to the manufacturer provide curves to assess sustainability. Centrifugal pumps are widely used in various industries due to their effectiveness. These devices operate using a set of rotation blades that generate kinetic energy in the fluid, thereby increase pressure primarily through centrifugal forces. This project, incorporating principles of reverse engineering, focus on the understanding the operation of centrifugal pumps and simulating their performance under varied conditions. It encompasses tasks ranging from the creating CAD models to comparing results with manufacturer specification, all with the aim of comprehensively assessing their sustainability.
Parameters to generate the geometry. The creation of the geometry was carried out in the Autodesk Inventor program. In the table, we can see the necessary parameters for the geometry, such as the inlet diameter and outlet diameter, and others. The final CAD model was a centrifugal pump.
Okay, for the geometry part, we have three of them, which are the most important. First is the housing, which contains and directs the flow of fluid through the pump, as well as converting kinetic energy into pressure energy. Second, we have the impeller, which is responsible for creating the flow and pressure within the pump by accelerating the fluid and imparting kinetic energy to it. And finally, we have the diffuser, which is responsible for slowing down the high-speed fluid discharge from the impeller, and it converts that kinetic energy into pressure energy.
Criteria for mesh generation. The main meshing characteristics are as follows: polyhedral mesh, surface measures, thin measure, and Prince layer measure. Prince layer measures were placed in regions close to the wall in order to model the interaction of the fluid and the wall. The design parameters present in the table were used to generate three mesh with a number of cells varying in the range of 900,000 to 1,500,000. Boundary conditions. First, physical conditions on the fluids were established, where the fluid is turbulent, incompressible, stable or steady, and has only one phase, liquid. Specification on the impeller. Here we can analyze the physical properties of water and oil, together with the Reynolds number. Calculate with the expression that can be seen on the top of the table. Models. The flow was simulated in the STAR-CCM Plus program with the model K epsilon turbulence model. The model was selected because it has high accuracy and good response in flows with high Reynolds number and with a J plus of less than 30.
In this figure, the area of the head obtained for a flow rate of 250 meters per hour can be seen in comparison of the one from the manufacturer. Likewise, we can see the difference between the computational time for each mesh.
For the mesh independency, we did three attempts, with coarse, base, and fine, with the values shown in the screen. For the selected mesh, we chose the base, because of three reasons. First, the number of cells is suitable for turbulent flows in pumps, which is the case. Second, there is a minimal efficiency and error difference between fine and base mesh. And finally, this mesh improved the computational time for simulations.
The polynomial behavior of the experimental curves for mineral oil and water indicates that an increase in flow rate results in a nonlinear decrease in the total head of the pump. This could be attributed to the system geometry, the viscosity of the fluid, and the system's resistance. For efficiency, it is observed that both water and oil exhibit similar behaviors. However, due to the lower Reynolds number caused by the higher viscosity of oil, it faces greater difficulty in flowing, resulting in lower efficiency. Additionally, it is noted that the efficiency curve provided by the manufacturer demonstrates the highest efficiency.
In this figure, we have the head obtained by the CFD simulation versus the one obtained by the manufacturer. There you can see a range in which the information obtained by both sources is located. It was generated by calculating the root mean square, which is 9.51%. By having 4 of 5 points within this range, it can be said that the data we got by the simulation is similar to those of the manufacturer. In the case of efficiency, an RMS of 8.98% was obtained. Therefore, it is observed that there are more points outside the range that however are very close to the lines that generated.
As we witness the dynamic animation of this pump handling both water and mineral oil, observe closely as the velocity magnitude in the mineral oil surpassed that the water. This compelling demonstration underscores the unique characteristic of these fluids. In this scene, handling both water and mineral oil, we can notice that the velocity remains consistent within the impeller as it rotates uniformly. Additionally, you can discern that the increase in velocity occurs from the center outward, extending across the radius of the impeller. This uniform rotation and radial acceleration contribute to a consistent and controlled flow. In these scenarios, it is crucial to ensure a high water relay velocity. This is because mineral oil, the most viscous fluid, tends to impede flow regardless of the flow rate, resulting in reduced velocity within the pillar. It is important to note that the fluid velocity should increase as it approaches the impeller core and decrease as it is near the shear muscles in the polar area. In this concluding scene, it is observed that some impeller plates move faster than the oil, confirming an early claim.
Now we have the Woolley Plus. The Woolley Plus is a measurement that provides information about the resolution of the boundary layer and the influence of fluid viscosity in the vicinity of the wall, where the fluid moves slower due to the friction with a solid surface. In this figure, we can see that the Woolley Plus of the oil is lower than the one from the water. It is because of the difference of viscosity. Oil has a greater viscosity that provokes the boundary layer to be thinner. It means that a shorter distance from the wall is required for the viscosity effect to be significant compared to water. With the absolute total pressure, we can predict if the pump is gonna cavitate. If the total pressure decreases slower than the vapor pressure of the fluid, it will evaporate, causing the generation of bubbles. The water, due to its higher vapor pressure, tends to present more cavitation in comparison to oil.
Absolute total pressure. The behavior of the total pressure is adequate. In the central part of the impeller presents low pressures. On the other hand, in the end of the impeller, we see the highest cavitation.
Well, so as a conclusion, the objective of the practice was reached, which was to be able to design and simulate the function of a centrifugal pump for water and mineral oil. It was corroborated that the performance of the pump decreases when the viscosity of the fluid increases. And finally, the water data was similar to the manufacturer according to the RMS.
Also, the fluid in the simulated pump behaves differently from the one from the manufacturer, which causes differences in the pump curve. Finally, the worldwide loss is mostly affected by the viscosity of the fluid used.